Students, this question is about a compounded DC motor. We have a compounded DC motor. Here is the circuit for the compounded DC motor, and this is long shunt type of compounded DC motors. And for this compounded DC motor, we know that the fundamental equation for the internally generated voltage is Vt minus, and we have Ia Ra plus Rs. So the first question it talks about is what is the shunt field current in this machine at no load. Now what it is saying that when this machine is running at no load, we have no load attached to the machine, how much current is being drawn by the shunt field winding. So now here there is one concept that I would like you to know, that for example this is the DC motor, it is rotating and we have connected it to the source Vt. Now in the examples we have seen that even when the motor is not loaded, there is a current that is going inside the motor, and this current is actually going to the field of the motor and also to the armature of the motor, and which is we calculated mechanical or rotational losses. We can calculate mechanical or rotational losses for the motor. But when we are considering in this question, you can see the core mechanical and stray losses may be neglected. This means that the armature current there will be no current going to the armature to compensate the rotational losses. So the only current that is going for this motor that is given in this question will be the field current. So and we can see that Vt is equals to 250. So If is actually the voltage. If we have to calculate If is equals to Vt over R of F. And what is R of F? It's the Vt is the voltage across here. So this will be R of F plus, and R of F is basically I will call it R of Ft total, and this is actually equals to R of F plus R adjustable. So let's see if they have given the value of this R adjustable. No, there is no value for R of F, but there is another important observation here. When the current Ia is 0, so actually Ea will have the same voltage as the Vt voltage is here, because there is no voltage drop across Ra plus Rs. So we can say that in that case Ea is equals to 250 volts, and when the Ea is 250 volts, that is EMF, so at that case this is open to terminal voltage, that means it is open, this is no load condition. What is the field current here? It's 5. So 5 amperes, when If equals to 5 amperes, when the current is 5 amperes, then internally generated voltage is 250 volts, and this we can see from the graph, and that is how we have calculated this thing. Because if we would have calculated if he has given us the total field resistance, it would have been 5 amperes, but we had the graph, so we have calculated from the graph that at no load condition this will be the internally generated voltage. Now the second part talks about the motor is cumulatively compounded. Find its speed when Ia is equals to 200 amperes. Now for this motor we know that Ia is equals to 200 amperes. So for a cumulatively compounded motor, for the compounded motor we have this equation: Ia is equals to R A plus R series. So this will become 250 volts minus Ia, they have given us 200 amperes, and Ra plus R series. Let's see how much is the value of Ra plus R series, including the series winding. A compounded DC motor with compensating winding and internal resistance, including the series winding of 0.04 ohms. So the total resistance is 0.04 ohms related to the armature and series, and this will correspond to 242 volts. So now at 242 volts we are required to find out the N. But now in the cumulatively compounded motor, we know that a current IA 200 amperes is flowing here, and we also know that IF is flowing here. So the field inside the motor is due to this series winding also and the shunt winding also. So the effective field current, which means the total flux that is being produced, and the effective field current will be inside the machine. If you look at this, F effective is actually equals to F due to our shunt winding plus F due to our series winding and armature reaction minus. If we are neglecting this, then I can say that NF I effective equals to NF IF plus NS I series, which is actually the armature current. So the effective field current which is producing the flux, which is representing the flux being produced in the machine, is IF plus N series NF IA. Now IF is 5 amperes. Number of series turns, let's see, 3 turns, 1000 turns per pole on the shunt field and 3 turns per pole on the series winding. So this series has 3 and this is around 1000, and the current through the armature is 200 amperes. So this will become I effective is actually equals to 5.6 amperes. Now for I effective 5.6 amperes, if we go here and if we try to find out, so this will be almost, we can say that it is around 262 volts. So here then what we can say right now is that for an effective 5.6 ampere, the motor will have EA naught equals to 262 volts at the speed of, let's see what's the speed of this curve. This is for 1200 RPM. Now for the same effective flux and the machine constant, EA naught, the internally generated voltage is 242 volts. So what will be the new N? And this can be then calculated by our unitary comparison method, and it states that EA naught equals to K phi omega N naught over EA equals to K phi N. So this cuts, so the new value of this will be EA over EA naught to N naught. And what is EA? That is after 200 amperes the internally generated voltage. This is the same effective field what is, and this is 1200 RPM. So the value of N will be 1108 RPM inside the machine. So if the motor is differentially compounded, but what happens is, this was for part B, and for part C the effective field will be actually, both will be cancelling each other. So as they will cancel each other, then the effective field current we can calculate in this way. Only the sign here is changing. I effective will be 4.4 amperes. And like the previous method, when we perform the comparison and we go here and we look for 4.4 amperes, and we can find that the EA naught will be around 2 here somewhere, 236 volts. So this will be EA over EA naught into N naught. So EA will be again 242 volts for the same current, but the EA naught is now 236 and this is 1200 rpm. So the speed of the motor will be now 1230 rpm in the case of differentially compounding machine. So there is one important aspect also. We can see that this was the speed for increasing the load for cumulatively compounded, and this is the condition for a differentially compounded machine whose speed increases with increase in the load.